Currently, Rajesh is a PhD student at ETH University at Zurich, where he conducts research at the intersection of rendering and machine learning at Disney. He hasn't given up still his studies. That's fantastic. Rajesh worked 23 years at Walt Disney Animation Studios in various management and individual contribution roles, including incubating and managing the Hyperion rendering team and driving development of tools like XGen, Paint, 3D, hair, cloth, snow, and water splash simulation. He is credited with over 15 animated feature films from Disney Animation Studio, including multiple Academy Award winning films like Big Hero 6, Frozen, Zootopia, and Encanto. After Disney, he, has, he was a VP of engineering at Spirey Animation Studio, where he led the engineering efforts to enable artists to create high quality feature animation content using workflows and game engine technology. In addition to all his busy time at work, he devotes his time service to the community. Rajesh is actively involved in SIG as a reviewer, juror, and educator. He has also taught the popular online courses on ray tracing used to create stunning graphics for films and games and machine learning for the last 2 years with over 15 hours of video simulation. He's a great teacher, excellent instructor. I've attended some of his classes, and I'm sure we're all going to enjoy his talk today. And without further ado, over to Rajesh. Thank you, Rajesh.
All right. So I hope everyone can hear me and see me. I'm going to share my presentation with you. And thank you so much for the very kind introduction. And it's a pleasure to be here joining you in describing a little bit of the AI field, what promises it holds, what perils it might have, and then essentially like just a quick whirlwind introduction to the field itself and how to go about kind of addressing some of the issues that arise from using machine learning and AI, and then what kind of education and teaching we need in our universities to support that. So let's begin, and then I'll give another small introduction to myself. So I grew up in India. I was born in Patinda in Punjab, and my father used to work in the railways, and we would get transferred every couple of years. So I lived in a number of different places, and eventually ended up spending 4 years at Ranchi, where I got my first introduction to computers and computer science. And I was hooked from that time, just learning and understanding computers and making use of them for practical purposes. So these are a couple of pictures from the Silver Jubilee reunion. And it was a fantastic time we all had returning back to the school where we all got our start. And then after that, I came to the US. I did my master's, and then I got interested in computer graphics. I spent about 23 years at Disney doing all kinds of different things on the way, working on tools for different films, providing them with the ability to be able to make some of the things that had never been done before. Things like snow in Frozen and all the fur in Zootopia that you see. So it's a pretty interesting time. It never felt like a job. It was just having fun, doing very interesting things, putting them on the screen so that millions of people would watch them. And in the process, it was a great learning experience of like just understanding the production process, how 800 people come together to make a single film that takes 2 to 3 years to make. So after that, I joined a startup after doing all kinds of things at Disney. At the startup in LA, we were trying to build a studio in the cloud, and that is still going on. And around the same time, I got an opportunity to spend some time doing research. So research is at the core of my heart, and I love diving deep into technical topics and trying to understand them, and then eventually to be able to explain to others as well. So currently I'm in Zurich, in Switzerland. That's where I'm speaking to you from, my tiny apartment in Zurich, back to being a student again, doing some research in rendering and applying machine learning to rendering. So rendering is a complex topic with a lot of history. And then with the new machine learning techniques that are coming up, there is a good opportunity to apply those. So that's where my work is focused right now. So I also travel a lot, I teach a lot, I cook. So these are three of my hobbies that I try to practice as much as I can. And this has been an amazing opportunity to kind of come to Zurich, where you have access to almost all of Europe to travel and eat all kinds of food, and then participate in teaching. So I'm a teaching assistant for the computer graphics class, and alternate semesters I'm a teaching assistant for the machine learning class. So it's an interesting adventure after years of spending time in the industry to go back to school. So let's come back to the topic of today, demystifying AI. So this is something of a topic that I do some research in. I have studied machine learning basically from scratch on my own for some years, and then eventually when I came to the university, I'm kind of learning some of the deeper methods, some of the math behind all the things. So I thought it'd be a good opportunity to kind of explain to everybody like what this field is about, what promises it holds, and what you can do with it. So it's going to be slightly technical talk. Given the audience that we have today, I think it shouldn't be too difficult to understand what I will describe. So it's going to be quick, but it has a lot of content as well. So as you already know, the AI is everywhere, right? So if you use your smartphones, you have voice assistants, you have identity. If you have an iPhone with facial recognition, they all use some kind of machine learning based algorithms behind their interfaces. Hold on. A lot of people coming into the lobby, so I need to allow people to enter. Sorry, a little bit distracting. Even things such as like efficient use of battery life, how to optimize that. There's a lot of algorithms under the hood that operate kind of trying to maximize your battery life on a smartphone. If you use email, you already know about the spam filter where lots of spam goes automatically into your spam folder. So this is probably one of the earliest uses of machine learning techniques was to just classify email as spam or no spam. And then lately, there are grammar corrections as you type your email. There's autocomplete for text. In fact, sometimes completing entire sentences. So it's all there and you all use it. If you use a self-driving car, even not a fully self-driving car like Tesla, you have other cars that still use some kind of a vision-based algorithm to kind of keep you in your lane or to warn you if you kind of veer off or if your hands are not on the steering. So all these techniques, the underlying mechanism is some machine learning based inference that happens. You use your phones to take pictures. The pictures can be automatically enhanced. You can also do these days geometry capture via technique called NERF, where you can not just capture a single 2D image, but also the surrounding geometry of the objects that you are capturing. You probably use navigation for driving, directions, mapping, live view, AR, all kinds of things use AI. And banking for identity purposes and for fraud detection. Sometimes you would get a mail from your credit card saying that the purchase you have made is outside of a range or it is not a usual purchase that you make, and you would be notified of that. So there are some lesser known fields like agriculture that machine learning is being used more and more, like automatic watering and weed control. You have machine learning algorithms that, based on vision, can identify weeds and just target those to be removed or killed. And similarly, in e-commerce, if you shop online, you have recommendations based on your past history or the likelihood of you buying something similar that you're already looking for. So all these applications in ad tech that are ongoing in e-commerce. And similar thing for entertainment, for recommendations of movies that you like. In computer-generated imagery, you see a lot of AI being used these days for editing, for reducing noise in the film. So you are probably already using a lot of AI and machine learning, even without knowing, willingly or unwillingly, you're kind of being pulled into the direction of using all these things. So one thing I do want to mention, that AI is like a general term, right? So it has this word intelligence in it, and it can be hard to describe what exactly intelligence is. And we assume that whatever things a human can do, they are intelligent, and that's what we are trying to achieve. But that's why I don't like the term AI or intelligence in a way, because it's hard to describe precisely. As a researcher and a person who's based on logic, it's very hard to define these terms. Like, is it sentient? Is it? Does it have consciousness? Does it have soul? What does intelligence mean? So intelligence is a complex topic in itself, partly philosophical, partly mathematical. Like, what does it even mean to be intelligent? So for most of these purposes, we're going to use the term machine learning, where it makes things easier to describe mathematically, rather than intelligence, which is a loaded word. So why now? So I think these techniques, some of these techniques that we use today in machine learning, it is strange that in the last few years, this field has picked up. So there are three kinds of reasons why this field has picked up and has become more popular. One is the enormous amount of data available to us today, right? With all kinds of measurement devices and sensors and emails, all this data is out there now. And then to be able to make sense of this data, the normal algorithmic ways are not sufficient. So just the availability of this large amount of data makes it possible for us to do a number of things with it. Second is the faster compute and the availability of GPU from companies like Intel and NVIDIA. And these make things very useful, because if you look at how today's machine learning is implemented, it is essentially a lot of vector algebra implemented as code. And vector algebra means multiplying matrices and vectors. And GPUs are really good at that. So GPU originally started out as doing graphics processing, but NVIDIA at some point discovered that they are great for matrix multiplication. So most of the machine learning moved on to using vectorized mathematical operations on the computers. And this has made things even more fast and possible to do large amounts of data with the hardware that is available today. And the third is the internet and the cloud availability. So the internet kind of makes data shareable and available easily to a lot of people who can collect this data and scour the internet, collect all this data, and then you can do analysis, you can do research with that data. And then the cloud allows them to kind of not have to bring that data back into local storage, but keep that in a remote location somewhere in the cloud. So then it's easier to process. So that's why, like you don't have to spend as much money on the electricity and infrastructure. You can just have all the data and the compute be in the cloud. So together, these three things kind of make AI possible today. That in turn has caused all the advanced research groups to kind of focus on AI as a means of understanding this large amount of data. New algorithms and models are being invented and discovered every day. And then the final piece of the puzzle is like all this is useless without applying it to something that is useful to human beings or humanity. So, so those three things, like the internet, the data, and the compute, they make possible this advance in machine learning and that you're seeing now. Okay, take a little pause and allow some more people into the room. Okay, so as I tried to define earlier, like AI is something where you have machine perform tasks that require human level intelligence. So that's like a basic definition of AI. And ML makes AI possible by learning from data, and then it makes predictions from that data. So learning from data is the essential part of machine learning, and machine is learning from the data. And once it learns, it can then make predictions. So you don't want to use machine learning for things where you already know some kind of analytical solution. For example, if you want to use machine learning for finding out the time when you drop a ball to the ground, you can just use Newton's equations from laws of motion to kind of get that. You don't need to use machine learning. So if you already know how to do something with an analytic formula, you probably don't need to use machine learning. So machine learning is for kinds of things where there is a lot of data, you want to make sense of it, you want to make predictions from it. So that's the key difference between like machine learning and non-machine learning methods. So machine learning can be roughly divided into these three categories. One is supervised learning, where you have labeled data. So you collect a lot of data about, like, for example, you have a house for sale. So you would collect some features about that house, like number of rooms, the square footage, and location. And those are the three features. And then you will have a sale price as your label. So then you would go ahead and collect lots of data for houses in the neighborhood. And now you have a set of data that you know these three features: the location, the square footage, and the number of bedrooms, and then you know the prices. And then when you are asked to price a home that is in a similar neighborhood, you can give those three parameters, and then it will predict a price for you. So that's like a very simple application of machine learning, which is like you learn from data, and then you learn to predict the value. And unsupervised learning, on the other hand, is that you don't have the label data. So all you have is just this large unstructured data, and you're just trying to find out meaning and relationship between those data, which things are similar, which are large, which are small, which are a different color, which are placed differently. So it's mostly about meaning and relationships. And the third kind, which is not talked about a whole lot in the press, is something called reinforcement learning. So reinforcement learning is based on reward and feedback, where you have essentially a state machine where the actor, in this case, is trying to learn. And at each step, they have choices to do some action. And then based on that action, they may get some reward or punishment. And they learn to maximize that reward by just over time taking the right kind of action. So reinforcement learning is used a lot in games, a lot of it like the AlphaGo chess that that Google did for learning the Go game, where it reached very high quality of expertise in that game just by training it on reinforcement learning. So same thing can be used for video games. And it is kind of like a way where a child learns in this world by just experimenting and repeating things and getting a reward of some kind, either intrinsic or external. And then as they get better at maximizing that reward, they learn the objective that they have. So there's roughly three kinds of machine learning that are in use today. So if you look at the bigger picture of like how this all fits into the data science revolution that happened because of the availability of a large amount of data a few years ago, that kind of leads into AI and machine learning. And this is like a rough diagram of how things kind of sit together. It doesn't have to be necessarily like that, but this is kind of, you can think of it as they're all related in some way. They help each other, and they, like, you use all this data and data prep from data science, and then you feed it into these machine learning algorithms, and then you try to make predictions and gain insight from this data. So now I'm going to give you a quick summary of the current state of the art in the machine learning field, primarily focused on the neural network side. And then we'll look at some of these things in a little bit more detail on what they do and how they are built. So this may get a little technical, but I think I'll try to see if I can make it as easy to understand as I can. So before we dive into that, I think there are two crucial pieces of information or knowledge that you need to understand these things. One is something called a distribution. So this picture that you see here, it's a normal distribution, also known as Gaussian distribution sometimes, or the classic bell curve, because it has the shape like a bell. And you probably have seen this many times. You've heard of this bell curve or a normal distribution. All it means is that there is a lot of data, and they are identically distributed. They're not identical, but they're distributed in a way that is, they come from the same source, or they are about the same thing. So they are independently and identically distributed. So that's the main assumption around the normal distribution. And what it says is that there is a mean, mu, around which the data is distributed. And as you can see, this is a probability density graph. And as you go to the left, you have extremes on one side. As you go to the right, you have extremes on the other side. So as an example, take heights of males in India, for example. So the mean would be around, say, 5 feet 8 inches. And very short people will be on the extreme left, on the green side of this thing. And then very tall people will also be on the extreme, on the right side of the green things. So, and then things would vary according to the standard deviation. At the very center, where you have the mean, there is no deviation from the mean. You have the standard deviation of 0. And as you move farther away from the mean, you have standard deviation, which is denoted here by sigma, as 1 sigma, 2 sigma, or 3 sigma. So you must have heard of things like a process that has a 6 sigma. The 6 sigma just means that the error rate is so rare that it is 6 sigma away from the mean, which means like very, very occasionally, and those things happen. So that's how people strive for their manufacturing process or the business processes to be 6 sigma, because you want to be pretty rare in making mistakes in those cases. So anyway, so that's the thing about distributions. And you can think of, because when you have large amounts of data, you don't want to think about individual data. You want to think of the data as a distribution, as it is coming from some distribution that we don't know. So what we try to do in machine learning is we try to understand that distribution. And in this graph that you see here, the black graph is assumed to be your data distribution, and the blue graph is the normal distribution. So what we try to do in many machine learning algorithms is assume that the distribution is normal, and then try to kind of push your distribution so that it matches a normal distribution. So you want to kind of align your data distribution to a normal distribution. The reason we do this is because once you have mapped it to a normal distribution, like on the right side of this graph, then you can use the formula on the right to kind of just sample from this distribution. And you can sample one point, giving it a mu and a sigma, and then you will basically get one data point in this distribution. So once you can sample from this distribution, you can do all kinds of creative things like interpolating between different data points, or coming up with novel data points that are not in the data anymore. So I hope that is clear. So I think this distribution is a very important concept in machine learning, and it's just a quick tour of what it means. The second concept that is important is something called a latent space. So latent space is when you take your data and then you move it into some lower or higher dimensional space where you can't visualize it, you can't make sense of it, but it's there. And in this latent space, the data is organized in a way where you can make sense of it mathematically. You can do lots of different operations on it, and it makes things much easier to be operating in this latent space, or higher or other lower dimensional. But as an example of latent space, I think it can be a confusing term, but it's really kind of conceptually it's straightforward. So imagine you have this data, which is just circles on a plane, and you want to have some kind of a linear separation between this data. But because they are kind of arranged in a concentric circle, you can't just draw a straight line and say the triangles are above this line and the circles are above this line. But imagine now you mathematically transform this data into a latent space where it is easier to separate them by a straight line. So one easy way to do this would be to kind of just reorient this data where the center is at the center of these triangles, and then you map it radially based on the distance from the center. So then just using radial coordinates, you can transform your data into this form, where now you can just draw a straight line and say, okay, now I can separate these data. So it's a pretty powerful concept. This is, I'm showing to you in 2 dimensions and 3 dimensions, but you can do this in very high dimensional space and make more sense of the data mathematically. So one example of this is these are handwritten digits where people have written ones and zeros and nines in different handwriting, and what the goal here was to separate them as much as possible. So if you see them, again, this has to be done mathematically because computers can't really see. So you encode them in some higher dimensional space, and by the way you separate it and the way you kind of align their distributions, you can see that they cluster around some common theme. So all the ones are a little bit together, and all the twos are a little bit together. And wherever they are kind of mishmashed, and that's the area of confusion where an 8 looks like a 9, and that's normal because every data point cannot be separated. But moving them into a latent space is a good way of analyzing them. So remember those 2 terms, distributions and latent spaces. So what the latent space then allows you to do is basically you sample 2 points. One is on the left and the second one is on the right. And you can interpolate between those 2 points. And you can come up with new forms of data. And in this case, the data is a set of images of celebrities. And each of those lines kind of is doing the similar thing where you have somebody on the left, somebody on the right, and in between we are interpolating in the latent space and trying to come up with new faces. In fact, you can kind of mix genders and hairstyles and facial features, and they all kind of nicely interpolate. Okay, so how do we gain better understanding of what machine learning does in these cases? And you have probably seen something like this and probably written code to do this or done the math behind it. This is a simple linear regression where you have a bunch of points. You are trying to form a straight line that passes as close to these points as possible. And because it's not going to pass through all the points, you are going to try to kind of wiggle it around so that these vertical distances that you see, the dotted lines, that they are minimized. They're minimized not one at a time, but kind of globally minimized. So, and that once you globally minimize it, that makes it the best fit for that particular line. And the way you do it is you take the distance that is from the point to a line, and then you square the distance, and then you minimize that whole function as a whole. So the minimization part, in simple cases like this, you can do analytically by kind of just because when you square the distance, you get a quadratic equation, you differentiate it, find the minima, and you can then find the best fit line that way. In higher dimensions, when you have multiple data points with features that are in the thousands, it will be hard to do this analytically. So what we do is we try to fit not just straight lines, but also curves. So you want to fit it something like this in the middle, not exactly going through each point as you see in this degree 20 polynomial curve, but you want something kind of like a curve like this so that your network has a little bit more predictive power. So the way to do this is then do the same process that we do for linear regression. Essentially, you are trying to find a minima of a complex function, but you do this via something called gradient descent. So gradient descent is just a way to kind of do the differentiation and then set that to 0 and find the minimum. And to do this in a more numerical way, there are efficient methods to do that. So you can think of neural network then as things that basically you have inputs, you have weights, and you multiply the inputs by the weights in some linear form. So again, it's all linear here. And at this point between each of these nodes, you add a little bit of non-linearity. And those are called activation functions. Again, no need to memorize the term. As you go into the field, you'll learn more about that. Just to keep in mind that everything is linear here. It's just a linear expression of multiplication of weights and features. So at some point, you'll get the final result. And that is the final result that you're trying to minimize via gradient descent. So this is a more complex looking network where you can have more nodes. It's fully connected in the sense where each node is connected to every other node. So this is, again, just an example of how these things are structured. So this is a diagram. So one of my friends, she helped me draw some of these things more visually. So again, take your time. I think I'll share this presentation later with everyone. This is, again, just what I said in words. It's describing it pictorially, how a neural network really works. You feed in data from one end, and then that's called the forward pass, and you multiply all the weights and you get something out. And then you compare that to your label, which is like, hey, is this the right value? If it's not, then you adjust the weight slightly, and then you do the gradient descent, which is essentially differentiating and setting the gradients, and you ultimately arrive at this result where you have minimized the difference between the goal and what the network computes. So then I'll just go through the list of different kinds of networks that are there. So an autoencoder essentially takes the input, moves it into latent space, and then tries to reconstruct it. So you can imagine a network that is kind of squished in the middle. So if you have a latent space that is smaller than your input space, then you have this kind of a squishing mechanism where you're compressing the data into smaller number of bits. and then on the way back, you expand it again. So it has two parts, encoder and a decoder, and that kind of, the mathematics is the same. It's just the shape of the network changes a little bit. So it looks something like this, where you take your data, you compress it down to a smaller space, and that is then useful for kind of compressing. You can take an image, compress it, that's like 500 by 500 pixels, and then you can compress it down to like 10 by 10 pixels and then reconstruct it back. So that's a good way of kind of compressing your data. It has uses other than just compression, and there are variations of it that allows you to generate new data points as well. There is another kind of network called the convolutional neural network, which is a different kind of architecture. Again, still a neural network, but designed in a way where it captures features hierarchically. So you have very fine features that are captured in the first few layers, and then as you go down the path, you're capturing higher level features. So it's easier to show it when with something like this. So these are very well suited for image-based algorithm, also known as vision-based algorithms, where you have images and they kind of, each of the layers, they learn a different hierarchical feature. So initially it may learn just lines and colors, and as you go up higher in the hierarchy, it will learn other features as well. So the reason we do this is partly because it's a nice paradigm. You have convolutions that we understand better from other image processing techniques, but also the way the human eye works. And the other main reason is that the images can be very high dimensional. So if 100 by 100 image has 100 times 100 times RGB, so times 3. So those are the number of features that you are inputting per image. So that can be very high. So what this hierarchical method allows you to do is kind of treat the numbers as at a smaller scale as you go along the CNN. So next kind of network is the transformer. So transformer is very popular. In fact, it was actually invented at Google by one of the BIT Mesra alums. It would be great to have him come and talk, detailed talk on this. So transformers essentially are a network which retain previous values. So in the examples that you saw previously, it was just each data point was separate and it didn't have any relationship to each other. But this kind of network, the transformer, has an association of time. So you understand like what came before a certain thing. So these are great for things like translation and understanding words and sentences. So in this particular example, say the input sentence is the meerkats love watermelons. So what this kind of network does, it starts paying attention to what came before, and then it learns to kind of predict what might come after. So once you have this kind of network set up, you can give it examples like meerkat in one language is this, and the second language it is a different word. And as you kind of train this, it will learn to predict what should come next in a different language. So or the same language itself. So transformers are the basis of ChatGPT. So ChatGPT is very popular now. It's a model that is deployed by OpenAI, a company at the forefront of machine learning and large language models. And what they do is take these and train this not only on small words and sentences, but they've trained it on almost the entire internet, on scanned books, on recently on images. So it basically has almost every word that has ever been written on the internet. And not just that, but by this attention mechanism, they have expanded that so that it can pay attention to not just the previous few words, but previous entire paragraphs, and has a bigger kind of attention memory where it can keep the context alive for what you know and what you can learn. So as you feed it things, it kind of tries to figure out what is the next most likely word or sentence or paragraph that should come next. And that's what kind of gives it its magic, is just sheer amount of data that is trained on. I think it's like billions of parameters now. And that I think almost feels magical and as if it has a brain of its own, but it doesn't. So all it is doing is trying to predict the most likely next word, next sentence, next paragraph that would come from what you ask it, what you give it as inputs. So this is, again, same cartoon image, but now in a more professional looking diagram, which is basically the prompt that you give ChatGPT. It converts it into tokens. Again, machine learning or most computers don't understand words, so they have to be kind of converted into some kind of numbers format that computers can understand, and then you tokenize it and you have a vector representation of words and the prompt that you entered. You feed it into your transformer network, which has been trained on a very large language model, which is mostly the entire internet and printed books. And then they further train it through reinforcement learning, because a raw model like that, it can be pretty destructive. So again, remember, the model has really no sentience. It doesn't know what is appropriate, what is right, what is wrong. It just knows what comes next, or what is the most likelihood of some word or some paragraph coming next. So they train it further on reinforcement learning, which kind of puts rails around things where it won't do bad things, or it try to be just in the range of what humans would expect some chat program to respond. So you can think of it, this is a funny cartoon somebody put up on Twitter, which is this entire beast that has been trained, and then the purple person here is the fine-tuning part, and then the last part is this manual reinforcement learning step that happens. So that's what keeps the model more human-like, or more expectations of humans that it tries to meet. Otherwise, it can be totally wild. And you can see some people have tried to hack into, not hack is a very strong word, but they try to, through prompt engineering, they tried to kind of find the inner workings of a model that has given people some weird responses, even things like ChatGPT falling in love with somebody. And so there are instances of that where people have kind of tried to go around this rails that they put, and then every time that happens, they put more rails around it. So it's more acceptable in the society as for usage. So the next model I want to describe is something called a diffusion model. And diffusion model is at the heart of the image generation revolution that you must have seen, something like Stable Diffusion or DALL-E, that can generate images from basically just typing something, and I want to see astronaut riding a horse, and it would come up with that image. And they work on a slightly different principle, and they are modeled after thermodynamic diffusion process, where what you are trying to do is trying to create an image from noise. So it's pure noise, it's Gaussian noise that you start with. And the way they do it is to do a reverse process first. So you take your image, you introduce noise into it, and at each step you introduce slightly more noise until it is just noise. And then because you went through small steps, you can go back through those steps and recover that image from noise. But this is one particular noise. So if you change that noise slightly, and then you try to go back, and the idea is to get something similar to the original image. So imagine like every noise, just plain noise function, can then be turned into some image If you have enough examples of something, you can go back to that image or to an image that looks something similar to that. So here we have the slice of a watermelon. We add noise as you go through the forward diffusion process, add a little bit more noise until it's fully noise. And then you can reverse this process and then basically convert any noise essentially back to a watermelon slice. And if you vary the noise slightly, you will get a slightly variation of this watermelon slice. So you take this diffusion model, and then you can combine that with the textual models, and then you can then use the textual descriptions to come up with images instead of people having to actually create noise themselves. They can say, I want something similar to the image I'm giving you, or here is the text I'm typing, and then make an image out of this text. So it's pretty powerful, and it's used almost like I've been to some of the Discord servers where they have these models available, and they can be pretty compelling. So every day there's new methods being added to be able to control that, because as if you're an artist and you want a specific image, it can be pretty hard to get that, but then new methods are being added to improve the usability of these models as well. So that's the field of major models, state of the art, what's out there, what they can do. Seems pretty exciting. There are issues, and there are issues like any other field, ethical and social issues. So there is issues of bias and fairness, right? You can use this to kind of amplify distortion in information. You can make deep fakes or things that people didn't say or do. You can get a pretty good replica of a human being saying something or doing something that may not be true without their permission. So it's a big ethical issue. So beyond the kind of deep fakes and fake personalities, there is also this issue of fairness. Imagine like all this data is from the internet, from the books, and you are missing out the representations of billions of people who don't have access to the internet still. You don't know their lives. That data is not represented in the data that is trained for these machine learning algorithms. So as you do more and more of this, so all your algorithms, they get biased in turn, and because they are using data from the people who use the internet, even like their idea of beauty, their idea of proper behavior, that all comes from people who are already educated, people who have access to the internet. So it kind of leaves out a big group of people who don't have access, and that's basically is going to make the inequalities already kind of that are there, and those inequities kind of become even bigger if you don't pay attention to that. Then there's the issue of private data getting into bad hands, misuse of private data. Already artists are complaining that the images that they drew for the internet, they are being used to train this, so they are not getting any compensation out of it. So that's an issue. Like, how do you kind of do this in a way where the data, there are laws, but the research kind of moves so fast that people kind of tend to ignore those things. And then issues like who's responsible? Like if AI makes decisions and those decisions go wrong, who's responsible? Who's to be blamed? So that's an issue. We still haven't resolved that. It's going to come up. It's going to become a legal issue at some point. And also, we do understand the math behind these things. We don't fully understand like a single neuron in a neural network, like what is it doing? Like what can we do to fix it? Why are the values wrong? So we don't have a good understanding of how to kind of go deep into the neural network and fix something that is not working. And that may kind of cause people to distrust it when things don't work properly. So this is an example slide from the World Economic Forum, and this kind of lays out like all the main issues that happen with. Essentially, it comes down to data collection that is not distributed equally among people who kind of you make decisions on their behalf, but they are not included in the data. So then the biggest risk, which people worry about a lot, is like jobs. So jobs that will be automated, they will go away. And that is a hard thing. You can't just say to people like, oh, don't need your job anymore. So I mean, companies can say that as governments, as social institutions, you want to retrain people, you want to provide livelihood to everyone. So there are issues there, like what kinds of jobs will go away, and what kind of jobs will remain. How can we make opportunities for the people who lose their jobs to be able to kind of still do well in society, in life. And this happens in every era of like whenever big changes like that happen, there are jobs that do go away. And so at some point we had horses instead of cars, and horses went away and cars came in. All the people who took care of the horses, they don't have jobs anymore. So there are these kinds of transitions that happen from time to time. And I think if we are not prepared, there will be anger and revolt and unemployment. So all those social unrest that we need to keep in mind for. So if you worry about your job, I think it's not that it's going to happen overnight. It takes time for these things to come in and be deployed and be trusted. But you can be ready, you can learn, you can train, you can get better at other things and then try to change. And for some people, it's really hard. And, it's going to be a challenge coming. So the best thing you can do is transition into new skills. And I guess most of the people I'm talking to, they are of an engineering bent. They can learn new things and they can transition. They're not as different from what you do today. It's a easier transition for engineers to kind of move into different fields. So these are like just a variety of different areas where work goes on in machine learning. And if you have been a software engineer, or a DevOps engineer, you can kind of easily move into one of these roles by a slight bit of training and learning on your own or through some continuing education kind of courses. So I'm not going to go over all of these jobs, but I think they're at the lower row. There is these ideas for like what these jobs kind of entail, what you need to do and how you can be prepared for them. But there are others as well. I think in the application side, there are more. So this is more on the engineering side of the machine learning systems themselves. But on the application side, it's just an open field, right? So it's all based on creativity, what kind of applications you can come up with. There are hundreds and thousands of startups kind of just trying to see where they can apply this. So the large language models that I described, the diffusion models that I described, by themselves, they are useless. It's the application of them to something that you can do that is the most important part. So how do we go about teaching these things, and how to learn new skills? So universities would need to offer new courses and programs. So they have to be a little bit more hands-on, more practical, right? So the best way to do that is to collaborate with industry. A lot of universities do that very well, where you are trying to solve some real-world problems with an industry. It's not just theoretical knowledge, because so if you look at the kind of number of people who do machine learning research, that is small, right? So you're not going to do machine learning research. Most likely, you are going to use machine learning to do something else that is profitable. So for that, you need to kind of collaborate with industry, kind of find out what is the latest stuff that needs attention, how you can rethink current solutions to make them more efficient or useful. And one thing I think universities could also do is like allow students to use the latest tech. It doesn't help them if they are kind of sitting in their computer labs with 10-year-old computers trying to get a large model run. So I think give them access to the GPUs, to the cloud, to these existing new models, and then teach them in a way where they are not like years behind the industry. So they are just closely following the industry and whatever model the industry uses. I think if they can practice on those, and all these models, they can be scaled down and you can try them out at a smaller scale. In the cloud, I think if a university can just partner with a cloud provider, go to Oracle or Microsoft and say, hey, for my students, I need 100-hour GPUs time, 100-hour compute time in the cloud. I'm pretty sure they'll be happy to oblige. And the other part is this applied ML, where you are not just working in computer science, you are working with artists, you are working with chemical engineers. You're trying to solve problems in other fields with your expertise in machine learning and their expertise in their field. You can get together and solve problems that are kind of hard to solve. And then you also need to provide continuing education for experienced professionals who may want to come back to school and learn some new skills, and people who have been out of school for a long time, and they may need to come back and then learn a little bit more from what's going on. So that's some of the ideas around teaching and learning of new skills. I think that's all I had. And it's right on time. And I don't even know how to do Q&A on Teams, but let's see if we can figure out.
Thank you, sir. Thank you for a wonderful insight. And I'm sure it would have been a very good session for everybody else here. Everybody, you are now eligible to pose the questions. So you unmute yourself by raising your hands, and then you can ask the questions. Any questions, anybody?
Good afternoon, good evening, sir. I don't know what is the time there. This is
it is evening.
Yeah, this is Dr. Vimal from EC department. So it was very interesting talk. There are a few questions that I want to ask to you. That what is the role of sensors in the advancement of this AI field? That is the first question. And can this AI technology can help us to predict some natural calamities like earthquake and other, maybe with some accuracy?
Right. So I think the sensors are a way of collecting data, essentially, right? So you can think of like humans. We have sensors. We have eyes and skin that kind of sense the outside world. So similarly, like the mechanical sensors or optical sensors that you have, you place them in different places and essentially collect data. So think of them as data collecting devices, and with the IoT, Internet of Things, you can have millions of these, and they can kind of collect a bunch of data. And more data you have, the better it is to train. And then again, the main thing is then what do you do with this data? Do you have a problem? Do you have an insight that you want to find out? So there is like, for example, like there's this moisture sensing devices that are tiny. You can buy them, you can place them around your home. And if it senses moisture, and you can see that like it's not raining and you have moisture, and then it means something is leaking in your home. So these are just a very small application. This may not even need machine learning, but imagine if you're trying to do this at a large scale, where you're trying to find out like emergency situations where water level has risen to some height and you have some moisture sensor there. So you can, I think it's limited by what kinds of applications you can think of, but otherwise it's just think of it as a data collection device. And then for the other question you had, so yeah, so machine learning is being used for like these kinds of things to predict landslides. So I think for that, you need to partner with people who kind of know their field. So you can't just build a model. You have to understand, like, so for example, what causes landslides, what are the different factors, and what are the early signs of a landslide. And then you place the appropriate sensors in those places. And then you learn to predict, right? So otherwise, if you're just going to go, and that's why I mentioned, I think you need to partner with the expert in the field who kind of can give you the parameters of prediction, and what makes a good prediction is pretty very important.
Thank you, sir.
Hello.
Yes. Yes, Mr. Devendra.
Yeah.
Hello,
Yeah.
sir.
Good evening, sir.
Hello, sir.
Am I audible?
Hello, sir.
Two
Am I
Yes,
audible?
Mr. Devendra, you are audible. Devendra ji, you are going. You please go on.
Sir, I
Yeah.
am
Good
doing my
evening, sir.
MTech in artificial intelligence as a specialization. So sometime my faculties told me that artificial intelligence is just a literature or a program. Just when we do a program, it performs some function, that it is a program. It is not an artificial intelligence. They said it is just a program. They call artificial intelligence as a literature. Sir, I am doing my
Okay,
specialization in artificial intelligence. Sir, please clarify. Sir, please
right.
clarify.
So it is, well, it is a program. It's predicting data, but I think I said earlier in my talk, like, I think, don't think of it as intelligence. So it is not intelligent, right? In this common way that we describe intelligence, it is, but it doesn't mean that it's not useful. And I don't understand the literature, what you mean by that, but it's not literature either.
Yes, sir.
Hello. Yeah.
Hello?
Yeah, sir. Thank you for the presentation today. I have a question.
Go ahead.
Yeah. So the natural intelligence, what we human have, and the another thing is this artificial intelligence, and the connecting link is the features which natural intelligence have, like emotions and say survival strategies. So are we in your field in US or in your universities, are some work going on to connect the memory with emotions?
So it's a difficult question, right? So what makes us intelligent and human is not very well describable. And to make machines intelligent in the sense we are, you need to be able to describe it precisely. And if you're not going to be able to do that, then there's not going to be intelligent, as we say in colloquially what intelligence means. But that doesn't mean that it's not useful, right? So we have, like, for example, birds fly, and we understand how they fly, but we don't build our airplanes exactly like birds. We take some lessons about aerodynamics, and we take some lessons about weight, but we don't build airplanes that move their wings. We use different principles of science because we are able to describe that physically, how something can fly, and we build our plane. So, but that doesn't mean that the airplane is useless if it cannot fly like a bird. So it doesn't have to mimic human intelligence to be useful. It just has to do the work that we need to do, right? So that's like the kind of things that the researchers are thinking about are not trying to force intelligence into machines like we do. We don't even understand how our brains work fully. We have some idea, but it's not very clear yet. So in the meantime, what we can do with the machine learning is to be able to kind of give it all the kinds of data that human beings get. Like we read, we have language, we have vision, we have sensory touch, we have locomotion. So all this way of how we interact with our environment, we can just give it all the data that it needs, and then try to predict from that how things will go. And then regarding emotions, we again, if you look at any kind of a personality test that is given in MBA schools or when you get hired, you essentially get divided into 7 or 8 categories with different strengths in each, whether you're combative, whether you're helpful, and you can assign the same kind of traits to a chatbot, and you can kind of use them as levers to kind of make it more helpful. So if it's a servicing robot, it can be more helpful. If it is, for example, if it is not going to interact with humans, it doesn't have to be polite or nice. It can just do its work as efficiently as possible. So you can tune that down and do that. So there are some emotional things that you can understand and transfer back into the data models. But again, it's also a very ambiguous concept to be described precisely.
Thank
Any
you,
other
sir.
questions?
Yes,
Sure.
Surinder sir.
Hello.
Hi.
Surinder sir,
Yes,
please
sir.
go ahead, sir. Surinder sir. Let Surinder sir ask the question first. Sir, you are mute.
Thank you, Rajesh. It was a phenomenal presentation. Based on what I'm hearing is one of these days, these artificial intelligence will surpass the human intelligence. Although you said we don't know what is intelligence, but the way I'm looking at the complexity of the models and the prediction of which we can see and how they're working, based on that, our human intelligence cannot do that because the amount of data is so huge and the processing and then taking the next step in terms of predicting. Is it not beyond human intelligence?
That is correct. I think for very narrowly defined fields, it can do things beyond human ability. So already we saw like things like chess playing and the Go game. The machine learning models can surpass human ability, and the recent Chat GPT-4, I think it can also score in like 90th percentile or above in most of the academic tests as well. So there are, like, if you define your field narrowly, it can surpass human functionality. And that's what I was referring to earlier. I think you don't need it to behave like human in all forms, but just in narrow, useful capacities. And I think the way it gets better is by just using more data and then combining it up with new different algorithms and new different ways of using it.
Thank you again for the excellent presentation. Thank you very much.
Sure. Thank you.
Yes, Mr. Pathak, you may ask the question, please. Mr. Pathak, V. Pathak. Okay, Shivam, you can please
Hello,
go ahead.
am I audible? Am I audible?
Yeah, you are. Yeah, you are audible.
Hello, sir. It was very nice presentation here. I am Vishwambhar Pathak from BIT Jaipur. I am teaching here in Computer Science Department. I was a little curious about the interpretability models of CNNs.
Right.
I was trying to figure out, I reviewed some literature and found some layer-wise relevance propagation and others. But one question was that they help us find out the instantaneous dominance of feature recommendation also.
Right.
The purpose is to recommend the features that actually dominate the decisions.
Right.
So instantaneous decision is okay, but for the entire range of input, are they really reliable? That was a question, and I found that that could not be answered by LRPs and other features. So could you please, in a short comment, could you please enlighten my way? Thank you.
Right. So I think if you look at a CNN, I think the way it works is by using convolutions, and each convolution kind of reduces the number of input features and then kind of tries to convolve them into smaller features, and then assuming that when the weights they do stabilize at the end, that they will capture some of these salient features. So as you kind of reduce the size of these networks when you train, the first few features will be very, very kind of fine features. So it's basically just averaging pixels at that point. And then as you go farther into your stack of layers, you would have more structure that kind of starts coming up. And then convolution like this has been used for years in Photoshop to kind of do edge detection. These are like standard image processing techniques. And what is different about this is because they are networked together, and because they have a goal of minimizing the difference from whatever the label is, it can learn what is important, right? It can learn what is important, but then once it has learned that, you looked at some of the examples I showed, like you can't make sense of most of it. You have a general idea of what it means. Even when you visualize it, it looks like one of the feature maps is about circles, and the other one is about rectangles, and one may be about color, but they're not as easily separable. So that's one problem with the latent space, that they have mathematical meaning, but as a human being to us, they may not have any meaning at all. They may just be there because of some mathematical construct. So it's very hard, again, as you said, like the interpretability is really, really hard topic, and it's an active area of research. And if you want to know more, I think I can forward you some papers, but it's a hard task.
Thank you so much, sir. How can I contact you for more idea on it?
You can find me on LinkedIn and then connect with me.
Okay, sure. Thank you so much.
All right, so I'll take 5 more questions.
Yes, we have 5 more questions from Shivam,
Okay.
Commander Rohit Ratan, Anupam, Krishnak, and Arnav. Shivam, you can go ahead, please.
And thanks a lot for such a amazing presentation. My question is related to the risks of the AI, as Elon Musk has been very much vocal about the risks of these AI, and he even went as further as saying as AI is one of the biggest risks to the future of civilization in the World Government Summit in Dubai. So my question is, how far is the future that Musk is proposing far from us, and should governments be really concerned and very much concerned towards the formulating such regulations for the development of AI?
Right. So there are multiple camps here that kind of talk about AI in different ways. So the risks that I outlined, so they are real and they are here now, and I think we need to solve for them first. The bias risk and the job loss and things like that. I think what Musk and other people in that camp they talk about is something called singularity. So singularity is an expression they use when AI intelligence level kind of surpasses human beings, and then it's able to self-replicate and work on itself to improve itself. So they say, like, so this happens at some point, we reach human level intelligence, and then AI can improve itself, and that part can happen very quickly, almost overnight, where AI reaches a level of intelligence that we cannot even fathom. So, for example, like say a comparison between ant and us, an ant has no idea of like what even anything is, and so it would be a similar level difference when this singularity hits. So that seems like alarmist to me, and it seems very far away. So I think despite all the hype, you have to remember that these things are mathematical in nature. They are predicting from data. They are not intelligent. They are not sentient. They have no goal or purpose unless you give them something as human beings, right? So having said that, I think there is also some emergent behavior that happens, right? So it's not just doing a lookup or not just doing a search. It's combining things in different ways from data and presenting it to you, which to me is a little bit more like human beings. It's not exactly that. It's not intelligent, but this is what we do. We take all of our experiences that we have had in our life and we try to kind of distill it into a single decision that we make. So that's like, in that way, I think they can be similar, but the kind of future that Elon Musk predicts, I think that's very, very far away. But the other risks that are there about job losses, unfairness, bias, inequity, they're all real. They're here today, and I think we should solve for that.
Thank you, sir, for your answer.
Sure.
Yes, Commander Rohit, you can please go ahead. Rohit Ratan, if you are there. Okay, Anupam, please go ahead.
Yes, sir. Sir, first of all, thank you for this great session. Sir, is AI dangerous for our future jobs? And what is very useful, AI mind या human mind?
Well, it depends on what you do. Like if it is, so nothing can take your job away if you are always learning and adapt to things, right? And even if it goes away, you find something else to do. So it depends on where you are in your life, in your career, and to me, it doesn't matter. Like it takes it away. So don't be afraid about any of those things. I think you can adapt, and people do fine. So,
sir, one more question. Is in this current situation, which technology we should run?
When you say technology, I think that's a big word or field. But if you're trying to learn machine learning, I think there are two aspects to it. I think so. You don't want to learn like inner workings of a neural network to a research level unless you're going to be a researcher, right? So you want to learn how to apply these things to problems, and that's like the mistake people make. I think they think that knowing the math behind it is going to help them. It doesn't. I mean, it does to some extent that you want to kind of know how they work, but if you're not going to be a researcher, you should focus on the application side. And for application side, you can download any model, you can build something on top of it, right? Say for example, you want to build a personal assistant that can help people learn, like a tutor. So you take this chat GPT and then you kind of give it enough prompts, so then it starts behaving like a teacher. You can have that and you put a nice web interface onto it and give it to kids and they can learn. So you can specialize one of them for being a travel agent and it can answer travel related questions. You can kind of bound it by having to answer only travel related questions and do something else, and then make a web app that can talks to that through the API. So these are all applications. So they don't require you to understand the inner workings of it. They just, you should know how they generally work and how you can attach to them, how you can query them. So that's more of a standard software engineering API thing.
Thank you, sir, very much. It is very helpful.
Arnav, please go ahead with your question in a short and sweet way.
Yes, sir.
Arnav.
Thank you, sir, for yes, sir. Am I audible, sir?
Yes.
Hello. Yeah. Thank you, sir, for the wonderful presentation. Sir, I am an inquisitive second-year student from BIT Mechra, and I have just started learning about AI. And I have been reading a few papers of Michael Nielsen's and about deep Q learning and other things. And so, can you please guide me or tell me what were the things that you started with? Were it like projects that you directly dealt with, or you read many papers or some books about from where you gathered knowledge first and then you used it? So please, can you give a roadmap so that I can also be
Right.
at equivalent place to you or like that? Yeah, thank you, sir.
Right. So I think everybody's journey is different, because I learned this like pretty late in life, but I also have a good foundation with math and with vision things, in particular with graphics. So based on whatever your background is, I think you're going to start where you will learn the quickest. Because if you're learning on your own, I think you want to find a quick path to kind of relate to what you know already. And then you can kind of, after you have done that, then you can go back and learn the entire basics. And then if you are into research, then you can start reading papers. But any good introductory course on Coursera would be very good. I think it'll give you a good overview of the field, kind of like what I did, but with more math and more examples. Once you have done a basic course, and you can see what kinds of things you're drawn towards, what kind of things you like, and you can seek out, again, just Google it, and you'll find a lot of resources. The good thing about this field is there are many resources out there. I think all you have to do is find like search it, and then you'll find it. And then regards to like practical problem solving, that is also something you can make up problems for yourself, like tiny little toy problems. The one issue you will have is, like, if you want to train with a lot of large amount of data, you will need computer and storage. And initially you won't have that. So you can either get access to the cloud, or you can use toy examples. I think the smaller data set, they kind of teach you enough, so you don't have to kind of use big data for everything. So just follow these kind of rough guidelines, where take an introductory course and find out what you like, and go more. And then if you want to go back and kind of refresh your basics in linear algebra, probability and statistics, and then Python, data processing, and all those. So you want to have a good mixture of practical and applied.
Thank you, sir.
Sure.
Pratik, please go ahead. And then one last question from Rohit. Yeah, Pratik.
Hey, thank you for the great session. I have a small company, a small IT company I've been running for the last 10 years doing software development work. And I see this as a game changer. I believe there will be very high level programming languages in the future. There was a demo video by Microsoft that I saw where they used a library called 3JS. The prompt would be build a solar system. It would put the 9 planets. The prompt was put 1,000 stars on the scene. It would do that. And then it said, add a belt around Saturn, and it would do that. So I guess this is just the beginning of what we can do with ChatGPT. There are going to be very high level programming languages built using this in the future. So my question is, how can we as startups start now to build and monetize such opportunities?
Right. So I think if you look at these, like what Microsoft was showing, or even what OpenAI was showing, where you can draw a picture of a website by hand, and then send that as an image to ChatGPT 4, and it would kind of write code to replicate that, both visual replication of the drawing, and then as well as the content of the website. So all these are what I would call examples of something called prompt engineering, where you're not kind of messing directly with the large language model itself, but you are trying to prompt it to do something. And other examples that I gave earlier about like making a travel agent, or making a tutor, I think those are all examples of doing prompt engineering. So I think recently Khan Academy, it kind of integrated ChatGPT 4 into their product, and that is a version of ChatGPT that is closed off to extraneous things and focused more on tutoring. It also doesn't answer questions immediately. It asks the student to kind of break it down into smaller steps and guides them through solving it rather than providing an answer. So that is all trained on top of what the model is. So that's like two ways to do it: is prompt engineering and something called fine tuning. And through the API, you can do probably both. So I think the question you're asking is like, what can you do to learn? Is like this kind of prompt engineering, and prompt engineering will also get easier. Right now, you have to kind of have some luck and know exactly what incantation to kind of type to make it do what you want to do. But there will be kind of guidelines. There will be kind of standard scripts for it to be sent, so that it kind of immediately reorients itself towards behaving a certain way. You have to kind of also know what your market is or what your expertise is. Like, what kind of things do you want to make? I mean, it's all limited by your imagination, right? Because the application area is where things will become practical. The chat GPT by itself, it's still just a demo app. So you have to figure out, like, what should I do with this?
Thank you. Thank you.
All right, last question.
Any more questions?
Last question from Mr. Rohit, please. If you are there.
Evidently, he's not there.
Yes, sir, he's not there.
Okay, so we conclude today's session with some wonderful. This is one of the excellent presentations we had, and you saw so much of interest. You have created so much of interest. I'm sure they want you to come back and give them some more insight into. And definitely, this is what I am seeing right away. So much of interest and excellent presentation. Not only that, you told us how the journey started, how it evolved, and how complex the models are, which I had never envisioned. But apart from that, what you have said, the practical application that we can focus on and how we can start from scratch. Excellent. Once again, many, many thanks, sincere thanks on behalf of BitMyNA. Thank you so much, Rajesh, and look forward to seeing you again.
Thank you for having me. It was a pleasure.
Thank you, Rajesh. Thank you. Appreciate it. We all love it. And we met you in Phoenix for the first time last hour.
Yes, I know. I remember that.
And hopefully you will be with us for many years to come and help us out.
Definitely. Actually, it was last year. This particular week we were in Phoenix. Yeah, maybe just right 1 year.
March 24th, we were in Phoenix.
Right.
Okay, thanks again.
All right, thank you, everyone. And then just find me on LinkedIn if you want to connect and ask questions more. We'll talk later. Bye.
Bye. Bye, everyone.
Bye, sir. Thank you. Thank you.
Hello, Rohit.